All right, welcome back everybody for the first afternoon session. It's my pleasure to have András Gilyén from the Alfréd Rényi Institute of Mathematics as the next speaker, who will tell us about a quantum speedup for approximating the top eigenvector of a matrix via improved tomography. Thanks for being here, András. The stage is yours.
Thank you. So I will talk about, indeed, a speedup about approximating top eigenvector of a matrix. And this is via an improved tomography protocol. Although this tomography protocol will be not as simple as the other ones that we have seen in the morning session. So this is more of a long-term algorithm, but it's at least optimal, so we know how much speed up a quantum computer can promise on this problem asymptotically. This is what I talk about. So the goal that we want to solve in this problem, in this talk, is finding the top eigenvector of a Hermitian or symmetric matrix M. And this has many practical applications in computing the page rank, ground states, dimensional reduction, etc. So it's used widely in practice. And so the input model is that we assume that we can query elements of the matrix M. And, well, maybe it's a dense matrix, maybe it's a sparse matrix, mostly focused on the dense case. And in such a setting, we know that one could do full diagonalization of the matrix, which takes roughly matrix multiplication time, which is d to the omega. Omega is this matrix multiplication exponent, which is somewhere between 2 and 2.37. But in practice, it's more like 3, because it's actually very complicated algorithms that go beyond the simplest. And for this reason, people use the alternative method, which only uses matrix vector multiplication, because the matrix vector multiplication is much cheaper. It's only d squared time. And the power method uses this to find the top eigenvector. And so here is just a sketch of the power method. It's a simple algorithm. And for concreteness and to compare numbers, we assume that the matrix has operator norm 1. And delta is the spectral gap below the top eigenvalue of this matrix. And so how the power method goes, it just samples a random vector v, and something like 1 over the gap times iterates the following, that it computes the matrix vector product mv and updates the vector v. And one can see that as the matrix M gets multiplied several times, the top eigenvector is raised to high power, and all smaller eigenvectors start to die out because the eigenvalue is much smaller than the leading eigenvalue, and they exponentially go to 0 compared to the top eigenvalue and the eigenvector contribution. So if one runs this algorithm, then the final vector is close to the top eigenvector with high probability. And this is how the classical power method works. And an observation is that if we have a random initial vector, then with the fixed top eigenvector, the overlap will be about 1 over square root d, because it's random. And in every step, the overlap is magnified by roughly 1 plus delta factor until it reaches overlap around 1 at the end. And therefore, the overall complexity of this algorithm is d squared over delta, because we just do matrix vector multiplications roughly 1 over delta times. And this is actually provably optimal when the gap is large. And there are some small variants that improve further the gap dependence quadratically, like the Lanczos algorithm, but still it's something d squared over square root delta. And if the gap is small, it doesn't really matter much. Okay, so now the question, can we speed up this very nice classical algorithm quantumly using some quantum linear algebra? So let's see how one would try to do that. Well, the first thing is we want to prepare this random vector as a quantum state. And fortunately, we can do that efficiently using these state preparation data structures by Kelenis and Prakash. So here we assume that we can write down some numbers in a classical memory that we can query in superposition. And under this assumption, with only logarithmic quantum memory calls, we can prepare the state. And I know that this quantum realm is sometimes a bit of a controversial notion, but note that already to get the matrix elements in superposition, we need something like that, something storage that we can create in superposition. And if you don't have that, you have absolutely no chance for a quantum speed up. All right, so now we encoded the state as a quantum vector. The vector is a quantum state. And now the next step is we need to apply this matrix M. And so how much does it cost? How much queries and time does it take? And there is a very much intricate way to block encode a matrix M using only square root D queries roughly. This was work by Guanghao Lo, and that was primarily focusing on Hamiltonian simulation, but we can convert it to block encoding with the QSVT, quantum singularity transformation framework. So it takes roughly square root D time to apply the matrix M. But what we really care about is the top eigenvector. So with quantum linear algebra, we can actually turn this matrix M to a much simpler matrix, which actually projects down to the top eigenvector. This is again standard quantum linear algebra, and the cost over here is only 1 over the gap. So we are at the stage at the state that square root D over gap is the cost of projecting down to the top eigenvector. All right. Now the problem is that my initial overlap is very small, roughly 1 over square root D. So I need to amplify roughly square root D times to get this projected vector. And then I need to read out this quantum state and convert it to some classical data. So I should do some tomography. And in this setting, the optimal pure state tomography has complexity D over epsilon. Okay. So if I combine all these algorithms, I get to D square over delta, and there is even polynomial dependence on the precision. Pretty bad. Like I didn't gain anything compared to classical. So that doesn't look so great. Now then we try to prove some lower bound on this problem. And actually we could prove a quantum free lower bound of D to the 1.5. So it's provable that if you have these matrix elements and you want to extract the top eigenvector, you have to make at least that many queries. But there is a gap. It suggests that maybe it's possible to have a quantum speed up. So is there any hope for this approach? And so the observation is that if we would somehow have a good starting state with a proper overlap, like constant overlap, then the amplification step is cheaper, and then we might have a hope for something like e to the 1.5. And I will show you how this actually can be realized. So this lower bound is the right complexity, and we can get there. So what is the issue here? Yes?
So why do we need to project pi, like V to pi? You can do tomography on pi directly if you can implement it. Like, how do you implement the projector pi that you define here?
So you have the matrix M, all the numbers you can query in the matrix entries. You create a block encoding of the matrix M, and that takes square root D queries. But the block encoding, it's the matrix M, but we know it has a gap. So we can basically do spectral gap amplification to push it all the way to 1. So the top eigenvector, top eigenvalue goes to 1, everything goes to 0. And then it's a projector now.
Okay. And then you need to go through V to learn this state. You cannot learn it from pi itself, like from this block encoding.
Well, essentially, the procedure will do that, but then it's unclear how to do that.
Okay.
Just having executed.
Okay.
Okay, that's a good question.
Wait, so the last line says, there is an upper bound that's like D to the 1.5, but only if the stuff in the denominator is constant.
Yeah. So if I manage to get a state which has high overlap, like constant overlap in my state, then it's good. But a random state will not have that. It has much smaller.
So you're saying if you happen to have an initial guess for the state that had a good overlap with the eigenvector.
But we will do without it. So that's it. Like, okay, this is the hope.
Okay.
That okay, there is a hope if you have a good overlap, but how do you get there?
Yeah, good.
And this is the main issue that we tackle. This is the needle in the haystack. We need to find this overlap and somehow make it constant large. And well, yeah, that's a problem because quantum amplification is costly for this thing. But notice that classical amplification is for free. Just multiply your vector by 2 and basically free. So that's why the classical power method works, because classically you can multiply your vector, it's fine. Quantumly it's costly, but classically it's cheap. So what we will do is that we will follow this power method, and in every step we convert our quantum data back to classical, multiply by 2, and then re-encode as quantum data, because amplification in the classical world is cheap. So the idea is that as opposed to amplifying our state, we just treat it as a subnormalized state. So we managed to apply the projector to the vector v, and it's flagged with a success qubit 0. And we may be also unsuccessful when we apply the complement of the projector. And now this vector pi v has very small norm, but I just keep the state as it is, and I do tomography on this state, which is only 1 qubit bigger than my original state was. So it doesn't change much. And so what we rely on, that the power method is actually robust to small errors. So if I don't actually learn this vector pi v, but plus only up to some error, then Hart and Price show that it's fine, as long as you have the following two promises, that the error is not too large overall. So the L2 norm of the error is something like epsilon. And additionally, the overlap of the error with the top eigenvector is much smaller. It's only like epsilon over square root d. And why I need this requirement is because if the error is much bigger, the overlap is much bigger in this initial direction, it could happen that your random vector that you started with, the error completely cancels the overlap. It makes it 0. And you want to avoid that. And if you have such small overlap, then you avoid canceling the small, tiny needle that you are looking for. And the overall error makes the vector still small, and you can just amplify this classically. So what is the key technique behind is that we develop a new pure state tomography procedure that has such guarantees. It has small L2 norm overall, and also in any particular direction, it has even much smaller error. So that's the key. And this tomography procedure, it has improved statistical properties that I just told you. And at the same time, it doesn't really increase the overall complexity. So it still recovers the optimal d over epsilon complexity while having these very nice statistical properties. And that's the key. So this is the skeleton of the algorithm. And so now, maybe if you have any questions here, because I will move on to the tomography part. The next slide. Yeah, this is clear, then I move on to the tomography part. So now it's I will build up to this new tomography algorithm in a few steps. So the first step is that actually you can estimate the absolute values of the amplitudes very efficiently, only doing computational basis measurements. And the reason behind this is this Okamoto-Höfning bound, which is a slightly stronger version of the Chernoff-Höfning bound that you probably all know very well. And it's slightly stronger. It says that if you have a random variable bounded between 0 and 1, and you take n samples and take the empirical average, then it will approximate very well not only the probability p, that is the expected value of this random variable, but also the square root. So if you take the square root of the empirical mean, that will be close to the actual square root of the true mean, and exponentially close to that, like in Chernoff-Höfning. And this is stronger because p is very small. Like most amplitude will be very small in your quantum state, and therefore the probability of seeing a particular coordinate will be very small. And then the square root of p is much bigger than the p. So it's a much more precise estimate for small values. That's what it says.
Is there anything special here about the exponent and a half? Would this be true for like p to any power?
I don't think it will be.
Okay.
I think yeah, this is special.
Very small kernel hopping where you have a p 1 over p on the denominator? So yeah, I mean, yeah, so yeah, it's the sharpest one. If it, as opposed to a small p.
I mean, it's pretty sharp. I mean, if you take a general enough version of channel clustering, then plugging in numbers, this actually follows from it, but it requires some work.
All right. Oh, yeah. This is only bounded.
Yeah,
It's not binary.
yeah. Doesn't have to be
Yeah.
0, 1. Could be, but yeah, doesn't have to be. Okay, so this is the concentration inequality that I will use, and what it tells me that if I have a quantum state, and once again this quantum state has the form that it has a flagged part which I care about with 0 qubit, and with 1 qubit there is some other state which I don't care about at all. So I just put a dot there, meaning that you shouldn't worry about it at all. I don't care about that part. So what you do is just have this state phi, which contains psi as a subnormalized part, and just do computational basis measurements. And SI denotes the frequency of measuring 0i. So the first qubit measured being 0, and the second, and the key part of the state has index I. And SI is just the frequency of such measurement outcomes. And your estimator will be just the square root of this SI number. And because of this concentration inequality, we have that with probability at least 1 minus delta, it gives an epsilon approximation for all the absolute values of the vector. So this is a very simple procedure, just computational-based measurements, and gets you estimates of the absolute values of the amplitudes. Okay, so this is step 1. Now, step 1 is using conditional samples and the reference state to do some improved tomography. And so conditional samples mean that now we have one more additional qubit. It's in the plus state. So if my qubit, my quantum state is a superposition of something marked with a plus state and something marked with a minus state. And with the plus state is what I want to understand. And with the minus state is a reference state, which is basically uniform superposition over everything. So this is a reference state that I use to understand the first half of my state. But because it's in a coherent superposition, I can do some nice things, including recovering the phase of psi and so on, which otherwise would not be possible. So once again, what one does is just measures this in the computational basis. And so notice that if the ith coordinate, the amplitude, I assume that psi is real for this stage of things. If psi I is positive, then it will constructively interfere with this uniform superposition, uniform 1 over square of the amplitudes when I measure the 0 part in this plus state, otherwise with the minus. And then, depending on that, I can decode the sign of the amplitude, and then, so this is a slight extension of the previous one. I don't only recover the absolute value of an amplitude, but also the sign information by comparing to this reference state. That's the key idea of this improvement. And actually, this can be extended to also complex states, and this was in our prior work with Approximating, Cornelissen, and Nancini. But I need more. This is not good enough for me. So this was the stage before. It still gives you optimal complexity, but not good enough statistical properties. And now this is the key where I use this reference state, which is much more fine-tuned for my actual state. And what it requires that I have a reference state that is basically coordinate-wise an upper bound on my state, and also not too small anywhere. So this reference state I could just, for example, do using the first algorithm, the computational basis measurements. I just get a good estimation of the absolute amplitudes, and I use that here. And so it will be a state that is close to the absolute values of my true states, and then this inequality can be satisfied. Okay, so now I have this reference state. And in this slide, I forgot about the subnormalization. Just psi is a quantum state of norm 1 for simplicity. So it's a conditional sample. If my first qubit is in the plus state, I get the unknown state psi. And if my first qubit is in the minus state, then I have the reference state attached. And it's divided by square root 2 to make it normalized. And I only measure, in the computational basis, this state. And so what's the procedure is that once again, I measure this state in computational basis and denote by SBI the frequency of measurement outcomes BI. And I define my estimator the following way. It should be just S0j minus S1j divided by the reference state at that amplitude. That will be the jth coordinate of my estimator. And what I claim that this is an unbiased estimator of the real part of the state. One can similarly modify a phase and then gets also the imaginary part. So that's the same procedure. So recovering the real part is fine. And the additional property that is also satisfied by this, that in any particular direction, my estimator will be not off by more than epsilon over square root d. So overall, it will be an epsilon L2 estimator of my state. And also in any particular direction, it will be epsilon over square root estimator. So this is exactly the version that I need. And the very nice property of this, and what lets me prove these improvements, is that it's an unbiased estimator. The expectation value of this is the actual real part of the state. And to see why it happens, let's just see what is the probability of measuring 0i on the state phi, and what is the probability of measuring 1i at the state phi, and subtract them. So if you just compute this, it turns out that the first of these is just the ith amplitude plus the ith amplitude of my reference state divided by 2 squared. And the second one, because of this minus state, there is a minus sign coming in. That is just the ith coordinate of my state minus the ith coordinate of reference state squared. And this is just some like a plus b squared minus a minus b squared, and that is just ab. And there is some constant, so it just actually turns out that this is exactly the ith coordinate, the real part of the ith coordinate times the ith coordinate of my reference state. But that is the reason why I have to divide by the reference state amplitude. And this way I get an unbiased estimator. And so there are two important properties of this estimator, that the covariance matrix of a single sample will be upper bounded by 1 in absolute in operator norm. And also the outliers are not too big. So I might get, because I divide by the amplitudes of the reference state, it means that I might output a huge amplitude for a single estimate. But it cannot be too big, because I ensured that the reference state is never too small, and therefore an individual sample might give me something bounded by square root d over epsilon in total. So I might have outliers, but I take many, many samples, and the outliers are averaged out, and the covariance was small to begin with. And then if you apply some more advanced consolidation inequality, it's called the Bennett-Bernstein bound, and it gives you this thing that I showed you, that coordinate-wise it will be very precise, and altogether gives an epsilon L2 error. And we didn't know any prior algorithms for unbiased tomography, and know that to get this unbiased property, that sort of assumes that you can also reconstruct the phase. So some sort of conditional samples like here would be necessary for such properties. So it's very reasonable, but it turns out that it's enough to have conditional samples and computational measurements for this type of task. So this is the core of our algorithm, this new unbiased tomography procedure. And so now I can go back to the application, and actually this answers the question of Alex. This gives a new tomography algorithm which does not require being able to prepare the state, but only reflect around it. So only having access to the reflection around the state or the projector, that suffices for learning this state that we reflect around. And that's exactly what we do in this paper. So as input, you need some controlled reflection or a block encoding for this projector that's equivalent up to constant vectors. And that's what you do the power method. Basically, you sample a Gaussian random vector initially, and then repeat logarithmic many steps that you prepare this quantum state, project down, and do tomography, and amplify norm 1 and repeat. And this is just like the power method in general, and it will get very close to the top eigenvector after logarithmic many steps. And so why it is that initial overlap is once again only is 1 over square root d, and the error in the overlap is only epsilon over square root d. So as long as epsilon is less than, say, half, then you will not kill the initial overlap, and the initial overlap will start to exponentially grow until it reaches constant overlap with your state. And you need logarithmic many iterations. In every iteration is a pure state tomography, which requires d over epsilon work. And this is your algorithm, which is essentially matches prior pure state algorithm, essentially optimal, but no longer requires preparing the state, only a reflection around the state. So it's qualitatively new. There was no such algorithm before. And immediately we get our application to the power method, that we have some block encoding of the matrix M with spectral gap delta. Then we turn it into a projector and apply this scheme. And if M happens to be a sparse matrix with sparsity S, then actually you can do block encoding with square root S queries, and then you get this complexity, which in the dense case, it gives you the d to the 1.5 that I claimed. So this is the main algorithm. And we can extend it in the case when we have multiple eigenvectors. So maybe we have a degenerate subspace, and there's very little gap between them. So I can't resolve the differences, but I can still wish to recover the subspace of these two largest eigenvectors. It turns out that the algorithm can be perfectly modified to tackle this case. And so I can also phrase it as a problem of process tomography of a reflection. I'm given a reflection operator around the subspace of the dimension at most r. It used to be 1, now it can be some larger number. And the algorithm is basically the same as the power method. You will sample something like r or 2r independent random vectors and apply the power method for each. And the subspace that will be spanned by all these vectors all together will be a very good approximation of this projector pi at the very end. And this is the algorithm, basically. And because you just do the previous algorithm, but for r columns as opposed to a single one as before, the complexity is only r times bigger than previously. So it's about dr over epsilon queries to reconstruct this projector to operator norm precision epsilon. So this is like the best measure that you can hope for a subspace. And it's probably optimal if we prove a lower bound, which is dr plus d over epsilon. The d over epsilon part comes from state tomography, which is not optimal. And the dr, we didn't match it up with epsilon, but we believe that should be the truth. So we believe it's an optimal algorithm. And this should be compared with the unitary tomography algorithm that was recently introduced proved by Ha, Kothari, O'Donnell, and Tang. They have a procedure that, given a black box unitary, learns it to epsilon operator non-error with d squared over epsilon queries, or uses of unitary. Now we have less because it's a reflection around a rank R subspace, so it's a more restricted class of unitaries, and we get a speed up by the rank. And in the worst case, when this is a reflection around, say, roughly d half dimension, then you cannot do better, it seems, than resolve to the general algorithm, which was entirely in general. And once again, we can apply this thing to sparse matrices and finding top eigenvalue subspace, top eigenvector subspace. So we have some matrix M block encoded, and sorry, the gap should be delta. And we know that the top R eigensubspace has some delta gap below. We turn it into a projector and do process tomography on this projector. And once again, this gives you this dr square root s complexity, only r times bigger than before. Okay, now there is a gap in this argument that I always told you that the precision dependence is only 1 over epsilon. But actually, in my tomography algorithm, I had epsilon squared because it was statistical procedures and so on. So now how can you do this improvement? And that's this another ingredient in our algorithm, or in this tomography, is this iterative refinement. And this is a very cool idea, which comes from the early days of classical computing, like the 60s, that had limited precision. So you only had some finite, some few digit numbers that you had to work with, and still wanted to solve very large equation systems. So how can you do that? And this problem solves the very large equation system with only using small few digit numbers. And the idea is that in every iteration, it just solves the equation system to constant precision, and then computes the slack and iterates. So the idea is that first it finds an approximate solution, which is x tilde here, such that ax gets at least half closer to b than the trivial solution 0. So ax minus b is at most half the original vector length b. And then once you found such an approximate solution, we just update your b to be the slack, so that is just ax tilde minus b, and solve for this problem. And once again, half the precision there, and so on. And so if you repeat this procedure roughly log 1 over epsilon times, then you will get a very, very precise solution to the original problem that you cared about. And so this is iterative refinement for these classical computers. And yeah, the idea is just you sum up all the intermediate solutions, and that is giving you your ultimate solution, which will be very close to the thing that you wanted to find. And it turns out that you can do similar things in quantum computers, where your precision is not limited by the number of bits that you can have in your computer, but by all these tomography procedures. So it's a very nice way to use limited precision arithmetic to find a solution to an equation system, which is especially nice for quantum computers. And it again requires some QRAM to continuously prepare the states, but it just works as before. And actually, it turns out that this way of using HHL, you get some classical input and some classical output, but still can provide some polynomial speedups. And this is used in optimization problems, like in interpoint method solvers and so on. And this idea was pioneered by a group of people led by Tamás Terlaki at the University of Lehigh, who found this classical method and applicable here. And what I show here now, that actually these ideas that come from the dawn of classical computing can be applied and used in pure state tomography. And that is the way I can increase my precision quadratically by this iterative technique.
So sorry, I missed this. So in the context of the solid linear systems, why do you want to do this?
So if you do quantum linear algebra, then the problem is that you have your state, you input it as a quantum state, you manipulate, you solve as a quantum state the linear equation, but then you want to read out the solution.
Yeah.
And because of this tomography, it would give you some polynomial dependence on the precision. With the best method, it's 1 over epsilon precision dependence. But with this, you can recover logarithmic precision dependence because you do this only constant precise solution every time. So in the case,
it's a repeated tomography.
yeah. So in the case where you want a classical output, you anyway will pay a price of dimension linear at least because you have to write down the output.
Right.
And in that regime, it's very detrimental that you pay a lot for precision. But with this way, if you want a classical input, classical output, and speed up using quantum subroutine, then it's better to do it this way, because then the precision dependence becomes logarithmic. That otherwise seemed to be inherently polynomial because of tomography. And it's not because of this trick.
And it's an open question. Probably just not doable at all if you ask for logarithmic dependence on the problem dimension.
Well, yeah, presumably, unless you have some very restricted class of states that you can efficiently somehow measure and compare. Okay, now let's apply this to tomography, this refinement. So once again, the goal is that we want to learn some unknown quantum state psi0, and that we have some current estimate psi1. Psi1 is our best current estimate of the unknown state psi0. And we have some target precision epsilon, and we have some unitaries that prepare the two states, the unknown state prepared by a black box and the known state prepared by us. And we are promised that, sorry, not the target precision, not epsilon. Epsilon is our current precision. We know that our estimate is at most epsilon far from the ground truth. And then, well, we just, and we have some state preparation unitaries for the ground truth and our current estimate. One is a black box, one is our construction of our own. And so then we can create a circuit which, conditional on the plus state, either applies the first state preparation unitary or the other one, that is our own. And so what we do, we will use amplitude amplification to amplify this difference. So because we can prepare in superposition both psi0 and psi1, we can also subtract them in a way, but that will be a very small quantum state, but we can amplify it using amplitude amplification. So psi0 is close to psi1, so when we subtract them, it will be a very small vector, which as a quantum state we can amplify using amplitude amplification. But once we amplified, for the final state, it suffices to do only constant precision tomography, because it's magnified 1 over epsilon times. So any error that I make at this level of magnification is shrunken by a factor of epsilon when I put together everything, when I multiply it back. And so this is the idea that I only do constant precision tomography on this very much magnified state. And so in tomography, I only pay something like order D cost. But because I had to do amplitude amplification, that did cost me 1 over epsilon. So it's D over epsilon to do tomography at this level. And I managed to improve my accuracy by a factor of 2. And I just logarithmically recurse, and I get to the ultimate thing. And so now I get this Heisenberg-like quantum scaling precision, because the quantum part is done by amplitude amplification, and the tomography is only done to constant precision level. And now, and this can be combined with the, and if I do this constant precision tomography using the unbiased scheme that I showed, then it will be also an unbiased estimator with the same precision. So I get unbiased estimator and the optimal D over epsilon dependency on error and dimension. And this puts together all the ingredients in the algorithm that I told you. So the final slide is about shedding some light on the lower bound. Why is it an optimal algorithm? Why can't you do better? And for this, I will define a hard instance, which is for which it's hard to learn the top eigenvector. And the idea is that I want to hide d bits of information in the top eigenvector. So I pick a uniform random vector with plus minus signs for all the d coordinates. And I define a matrix, which is just this vector outer product. So it's a rank 1 matrix divided by 2d, so it's normalized. So the first part, this has operator norm at most a half. And I add some noise entry-wise. And the noise is much bigger. So this is a matrix with plus minus 1 over 2d entries. And the noise is much bigger. It's roughly 1 over square root d entry-wise. But it's IID Gaussian or whatever noise that I add here. And because of random matrix theory, we know that this noise doesn't add up very much. It kind of points in all directions. And therefore, this matrix have a small operator norm, and the gap remains large, even though the noise is a whole lot bigger than the signal that I hidden there. So this is the hard instance. And moreover, because of this perturbation theory of matrices, actually the top eigenvector of this perturbed random matrix will be constant close to the hidden information that I hid there. And actually learning this top eigenvector reveals most of the bits of the information that I hid in this vector phi to begin with. So recovering the top eigenvector of this randomly perturbed matrix still tells me most of the information about phi. And so this is the key to the lower bound, that basically to learn a sign of the ith coordinate, I need to extract a sign from these entries of the matrix, which are plus minus 1 over 2d actually. But the noise is much bigger. It's like 1 over square root d. So clearly, looking at a single entry, I have no clue what this sign should be. And to resolve this sign accurately, I would need classically roughly d samples to decrease this noise, which was 1 over square root d, to 1 over d only. I need d samples for that suppression of noise level classically. So for learning any bit, I need roughly d samples, which means d entries have to be read from the matrix. And I need to do it for most of the bits. So that means I need at least d square queries to this matrix classically. And that's not surprising that you need to read through the whole matrix classically. But the good thing that this argument also works in the quantum case. And the difference is that when I have some noise, the estimation is quadratically more efficient in the quantum case. So it only requires about square root d queries to these matrix entries to recover a single sign. But I still need to recover essentially all the signs to find this top eigenvector, and they are d signs, so it's d to the 1.5. And so, and to make this precise, we use some variant of the adversary method to argue very precisely about these things, but all fits together, and this proves that d to the 1.5 is the best we can hope for, and the algorithm that I presented gets you there. And so this is a lower bound which works in the case when you want only constant precision recovery and you have a constant gap. And under that very nice set of parameters, our algorithm recovers these up to log factors in the upper bound. Yeah. So this concludes the algorithm in my talk. Thank you.
Thank you very much, András.
Yeah, so what about trying to find it adiabatically? So, you know, you start in the top eigenvector of something in the form. Now, I think what will happen is that the runtime will go like 1 over the gap squared. But like in your count in that example, the gap is big. Am I missing something? Could you just try it? It wouldn't matter what the overlap is with the initial place you start. You know, just it might make sense.
So yeah, I understand what you say. For that, so what is the adiabatic path that you suggest?
Well, you have your final matrix. So you pick initially
just a project
something which is convenient, which is just some matrix, and you know the top eigenvector. It's whatever you find easiest to construct. And then you just interpolate between the two. Oh, wait a second. I'm sorry, because I have to show that the gap along the path is big. I made a mistake because I have to show the gap along the path is big. So, but still, okay, never mind. I have to get the gap along the path to be big, and I don't know what its relationship is to that gap. But it's very simple as a method.
Yeah, actually, I didn't think about this approach, but some variation of it could work. Yeah, it's a very good idea.
Any question?
Why can't OAA be directly applied to the initial state once we've created that projector? Is it asymptotically less optimal?
So what do you want to apply?
Amplitude amplification directly to that initial state with our constructed projector.
Well, yeah, the overlap is initially 1/square root d. So that was the first slide that on the algorithm that gives you a square root d overhead, which basically makes it everything go back to the classical complexity. So here is the first attempt. Yeah. So the initial overlap. Look at the last line. This is the complexity of this trial, and the initial overlap comes as like 1/overlap into the complexity. And with this, if it's 1/square root d, which is the best guess for a random state, if you have no better guess than that, it just gives you d squared, which is the classical complexity. So no quantum speed up there.
So what's the intuition for why this like read out, read back in? Is it really just you're saying that multiplicative factor is why we get?
Yeah, in each iteration, it basically costs only this d to 1.5 to do this. And after each iteration, you basically prune all the unnecessary information from your state and only get a small error. So you get the signal, which is the overlap with the top eigenvector, plus some random noise. The noise is small, so this will be a vector of operator norm, say at most half. You can multiply by 2, and you immediately multiply the overlap. But this is classical computation. Like you do it once and you are done. Whereas with quantum amplification, you have to redo it over and over. You can't save the intermediate result because of no cloning. So there you lose this advantage.
Further questions? That seems to be the case. Then thank you very much, András, again. And we'll reconvene after the coffee break at 3:15.